center in the solution of the astronomical triangle. For this reason, it is important to know what it is and how it is formed. Before examining the triangle in detail, however, let us see how its parts are used in finding a ship's position on the Earth's surface. We begin with the relationship of the observer to his zenith, which, you remember, is directly above him on the celestial sphere. Observe how this point follows him on the celestial sphere as he moves over the Earth's surface. Now, there is a reverse relationship for a celestial body. There is a point on the Earth's surface directly under the body which follows it over the Earth's surface. This point is called either the geographical position of the body or the subastral, subsolar, or sublunar point. If we have a star in this position, then we know that its geographical position, or its subastral point, is here, directly below it. At a certain instant of time, a navigator taking an observation of the star, that is, measuring the angle between the horizon and the star, establishes its altitude from his position on the Earth. Note that an observer on the opposite side of the geographical position of the star will observe the same altitude if he is the same distance from its geographical position. From this view, it is evident that any observer at the same distance from the geographical position of the star would observe the same altitude. Consequently, any observer on this curved line about the geographical position would obtain the same altitude reading at the same instant of time. This circle is called a circle of equal altitudes. If the navigator takes sights of two stars, he can establish two of these circles of equal altitude. When plotted on a chart of the world with their geographical positions as a center, they would appear like this. Each circle is distorted on the Mercator chart due to the expansion of the latitude scale. Note that the circles intersect at 2 points. As the observer is on both of these circles, the only positions which he could occupy to observe the two bodies at these altitudes at the same instant would be one of these points where the two circles intersect. It is easy to determine which is the position of the observer at the time of sight, as there is little probability that the navigator would have so inaccurate an estimate of his position that he would not know whether he was in the Atlantic or Pacific Ocean. However, if he should try to plot these circles of equal altitude from their geographical positions, it would require a chart representing about half the world. This is not practical, as on a chart with so small a scale, positions could not be accurately plotted. If we enlarge the scale of the chart, thus decreasing the area covered to one which could be used practically, the geographical positions of the bodies ordinarily would be outside the limits of that chart. Observe that the area we now cover is at a scale which can be used for plotting. However, the geographical positions are not visible. Only the bearing lines from the position of the observer toward the bodies. Also note that the segments of the arcs of the circles of equal altitude are nearly straight lines. For purposes of navigation, short segments of the arc are considered to be straight lines and are called lines of position. we can see that the bearings of the bodies, or of their geographical positions, can be measured by these angles called the azimuths, originating from the north direction of the meridian through the observer's position. However, to be able to use these azimuths, it is necessary to establish the observer's position as a point of origin from which to plot. The navigator at sea, however, does not know exactly where he is on the Earth's surface. After all, if he did, there would be no reason to observe the heavenly bodies. As he does not know exactly where he is, he must assume a position, or, from information available to him, establish a dead reckoning position and use this position as a base from which to work. The navigator assumes a position, AP, and from this point he draws a line representing the direction of the geographical position of the body. The direction of this line is determined by the azimuth of the body, which is one of the values computed when the astronomical triangle is solved. A line drawn through AP at right angles to this line represents a segment of a circle of equal altitude on which he has assumed himself to be located. For this assumed position, represented by the ship, he computes from the solution of the astronomical triangle what the altitude of the body would have been at the instant at which he made the observation. If the observed altitude and the computed altitude are the same, he knows that he is somewhere on this line of position. However, such accuracy in assuming a position is unlikely, and he will usually find that there is a difference between the two altitudes. If the observed altitude is greater than the computed altitude, then this condition exists, and you can see that he must actually be closer to the geographical position of the star than he assumed, and his line of position would be here at the solid ship. If, however, his observed altitude is less than the computed altitude, then his actual position will be farther away. The difference between these two altitudes, observed and computed, is called altitude difference, or altitude intercept, represented by a small a. It is a measure of the distance between the circle of equal altitude that passes through the assumed position and the circle of equal altitude on which the observer is actually located. The altitude difference, A, is an angular difference, but as each minute of angular difference on a great circle of the Earth is equal to 1 nautical mile, it is easy to plot the distance toward or away from the geographical position of the body. The computed altitude, hc, is obtained from the solution of the astronomical triangle, and thus the distance A can be established by the difference between the computed altitude and the observed altitude, which was measured by a sextant. In our study of the astronomical triangle, let us begin with an observer at the equator. His zenith would be at Z on the celestial sphere. We now turn the diagram so that the zenith of the observer appears at the top of the diagram, and therefore the plane of the horizon will be horizontal. This half circle will then represent the observer's meridian, and this half circle his celestial meridian. The north-south axis now lies in the plane of the observer's horizon. Let the observer move northward along the meridian. The zenith moves with him north along the celestial meridian, and the horizon also moves, keeping perpendicular to the line between him and his zenith. As it is more convenient for us to keep the zenith at the top center of our diagram, we allow the Earth to move under the observer. The line from the observer to the zenith remains vertical, and the plane of the horizon remains horizontal. Note that the north celestial pole rises above the horizon and the south celestial pole sinks below the horizon as the observer moves north. As he travels southward, the opposite condition results. Now the observer in north latitude observes a star moving on its diurnal circle, the path of its apparent motion about the Earth. Through this star we pass half a great circle which extends from pole to pole. This half circle is called the hour circle of that body. If stopped at any instant, the angle between the meridian and the body measures the hour angle of that body. The angle between the observer's meridian, that is, the local meridian, and the hour circle through the body is called the local hour angle. This local hour angle is always measured to the westward. If the angle is between the Greenwich meridian and the hour circle through the body, then the angle is called the Greenwich hour angle, which is also measured to the westward. Now, as the local hour angle always increases to the westward, it is possible for it to be greater than 180 degrees. This is not desirable for the solution of the astronomical triangle, so we use an angle which is less than 180 degrees. This angle, called the meridian angle, represented by the letter T, is named east or west, depending on the direction from the observer's meridian. The local hour angle and the meridian angle are the same except when the local hour angle is greater than 180 degrees, in which case the local hour angle must be subtracted from 360 degrees to convert it into a meridian angle, which is then named east. For example, if the local hour angle is 240 degrees, then taking 360 and subtracting the local hour angle from it, we have the meridian angle, which is 120 degrees east. From this, it can be seen that the meridian angle of a body has limits from 0 to 180 degrees, east or west of the local meridian. The method of finding the local hour angle of a body can best be illustrated on a diagram of the celestial sphere. While the more familiar concept of the Earth is the northern hemisphere, it is more convenient to use a diagram based on a view of the southern hemisphere. Therefore, we rotate the celestial sphere so that the south celestial pole will be at the center of our diagram. This permits us to have the upper branch of the Greenwich meridian at the top, and also to have west to the left and east to the right, as is the usual arrangement on charts. The Greenwich hour angle, a particularly important hour angle, is measured from the Greenwich meridian westward to the hour circle through the body in this manner. This angle is important because it is one coordinate of a body's position on the celestial sphere. To compute the local hour angle, let us assume that we are in longitude 60 degrees west. The sun has a Greenwich hour angle of 100 degrees. It can be seen that the local hour angle is equal to 100 minus longitude 60, or 40 degrees. If the Greenwich hour angle of the sun increases to 290 degrees, then the local hour angle becomes 290 minus longitude 60, which equals 230 degrees. We can see that to find the local hour angle when in west longitude, all we have to do is to subtract the longitude from the Greenwich hour angle. If the longitude is greater than the Greenwich hour angle, we must then add 360 degrees to the Greenwich hour angle before subtracting the longitude from it. Now let us assume that our position is 70 degrees east and the Greenwich hour angle of the sun is 35 degrees. To find local hour angle, we add these two values, which gives us 105 degrees. If the Greenwich hour angle increases to 210 degrees, we observe that the local hour angle is 210 plus 70, or 280 degrees. If the Greenwich hour angle increases still more to 330 degrees, we still find the local hour angle by adding 330 to our longitude 70 east. Only in this case, we must discard 360 degrees, which gives us a local hour angle of 40 degrees. We can see that to obtain the local hour angle when in east longitude, we add the Greenwich hour angle and the longitude east. To obtain the meridian angle T in any of the above examples, we know that it is the same as the LHA if the LHA is less than 180 degrees. Such is the case in the problem illustrated, where the local hour angle was equal to 40 degrees. In this case, T equals 40 degrees, and the name is west. But in the previous problem, LHA equals 280 degrees, and T equals 360 minus 280, or 80 degrees, and its name is, therefore, east.